Check, check. Hello, check. Today's session will be on bell violation and solving max cut problem using QA. Hello. Yeah. Am I audible? Sorry, what are you saying? So today is the final session of IBM Qiskit Fall Fest in Delhi. Oh, okay. I can speak low. IBM. Yeah. Okay. Okay. Today is Okay, today is the last session of IBM Qiskit Fall Fest. So we will be looking into solving the max cut problem using QAOA, one of the quantum algorithm, and we will try to violate this Bell inequality, which shows a pure quantum advantage over classical computation.
My mic is working now, Thiru. Can you hear me? Can you hear me on the call? Okay.
Dear participants, we will start in 3 to 5 minutes. In the meantime, please ask your colleague to join the meeting. Please share the meeting link with them as well. So we will be starting in 3 to 5 minutes.
So, good morning, everyone. So, welcome all of you to the day 3 of Qiskit Fall Fest 2025 at C-DAC Delhi. So, I am Krishna Sharma, project engineer working in the quantum domain at C-DAC Delhi, and I am delighted to have you all again today. Yesterday, we explored about how IBM is driving quantum computing and how you can use IBM Qiskit SDK to advance your quantum journey. So, today we are taking next some a little challenging topics. The first one is the Bell violation, and the second one is the quantum optimization and how quantum optimization is being used practically by industries across the globe. Okay, so first we will begin with Bell violation, a concept that beautifully demonstrates how quantum mechanics defies classical intuition and shows us the real quantum advantage exists in this with this simple mathematics. Then we will move forward to solve max cut problem using the QAOA, that is a NP-hard optimization problem, to see how quantum algorithms can approximate complex optimization tasks that are difficult to solve for classical computers itself. So these sessions will be led by Mr. Thirumalai, Knowledge Associate at C-DAC Delhi, who will guide us through all of these topics. Also, we will be sharing an attendance form towards the end of the session. Please make sure to enter your name exactly as you want it to appear on your certificate. Okay. So without any further delay, let's get started with today's session. So welcome Thirumalai, over to you.
Thank you, Christian. Hello, everyone. So, hope I'm audible. Thanks for the nice introduction. So, dear participant, today we will be going with two different sessions. One is violating the Bell inequality, which is Bell violation, where we can see how quantum can solve some problem which classical cannot solve. So we can also understand what is the quantum advantage means literally. Then the next session will be, we will solve max cut problem using QAOA algorithm, one of the quantum optimization algorithm. We will understand the objective of the max cut problem itself, and we will also understand what is QAOA and how to encode this max cut problem into quantum problem and how to solve using quantum algorithm. So let's start with the violation of Bell inequality first. In this session will be a very interesting session. We will be playing around with pure mathematics, and there will be no quantum jargon terms are involved here. But however, I have to walk you through first of all what is the problem itself in the beginning. Below that, let me introduce myself again. I am Thirumalai. I am currently working as Knowledge Associate at C-DAC Delhi. I have a MTech in quantum technologies from IIT Jodhpur, and also my specialization is in quantum computing. I also have 4 years of work experience at Amazon Chennai. This is my basic introduction about me. So let me give you some facts before diving into the session itself. We all know Einstein got Nobel Prize in physics, but most of us think that Einstein had Nobel Prize in general theory of relativity or special theory of relativity. But the fact that most of us didn't know that Einstein got a Nobel Prize in photoelectric effect, which is one of the phenomenal work that Einstein has done in the early work of quantum next to the Max Planck, which demonstrates the dual nature of light itself. This is one of the phenomenal work which further leads to all the other quantum related works in physics. So Einstein eventually got Nobel Prize for this photoelectric effect. However, most of us also didn't know that Einstein was completely disturbed by something called as a quantum entanglement. So he was not able to accept this quantum entanglement and the way of working itself. There was a newspaper article on New York Times at that time where Einstein started to attack the quantum theory. He even went and published a paper on how can quantum mechanical description of physical reality be considered as a complete. Einstein argued along with his colleague Podolsky and Rosen that there has to be something weird thing happening between this quantum entanglement, and he even coined that as a spooky action at distance. Sorry, this paper is popularly known as the EPR paradox, And EPR shows and EPR discussed that this long distance correlation, which we popularly now call as entanglement, it is incomplete, which makes some consequence in quantum mechanical concept. And they also tell that there has to be some hidden variable lies in this quantum entanglement, which makes this entanglement more weird. They also come up with two different concepts called as a realism and locality. So, what is realism? So, realism is something when there is an object, it has to be have some predefined properties, and it should not be get affected by any observable or anyone who measures from outside of the environment. As there is an example, let's say there is a ball, it should have some predefined properties like color, position, and shape, and it should not get affected by someone who is observing that object. So this called as a realism, which has to work in our physical reality. Then comes locality, which says that if there is an object in one particular environment, and it whatever the manipulation or any object that is influencing that particular object by environment, it should not affect the other object which is beyond its light cone. Which means that let's say I have one photon in earth, which is A, and I have another entangled photon along with A, which is B, which is separated like billions of galaxies away. If I perform some any operation on A, or if I manipulate any information on A, it immediately affects on B. So Einstein says that this information seems to be faster than light, but according to general theory of relativity, any object cannot faster travel than speed of the light. So EPR discussed that these two concepts as they argue these two, localism and reality, as a key concept that quantum mechanics is incomplete. And they also propose there has to be some hidden variable which we are not able to explain in the entanglement. So for years, no one able to prove that quantum mechanics is complete with proper definition for entanglement itself. After some day, there is a person called John Bell. He came with some paper called as on Einstein-Podolsky-Rosen paradox, which is the popular paper again on EPR paradox. He discussed in the paper says that he formulated a mathematical inequality such that it is not violating any of this locality and realism principle. And he also says that if this inequality is violated by any object, then that object or system is in quantum. So in this paper, he has discussed a lot of derivation in terms of physics and calculus and mechanics. So I'm here to make you simple about that particular concept. Let me discuss what Bell actually formed in his paper. Let's say we have a source which is of psi. This source continuously emitting particles in both the direction, and it is shared to Alice A, which is called as A, and Bob B. So let's understand psi is a source which continuously sending the particles to Alice and Bob. So now Alice can have two different measurement Q, which takes value of +1 and -1, and Alice can also take a measurement of R, and again it takes a value of +1 or -1. Same, Bob has measurement of S, which can take +1 or -1, and Bob also can have a measurement value of T, which also can take value of +1 or -1. With this setup, Bell form an inequality like this. Here, uh, 1 minute, sorry. So with this setup, Bell has formulated this particular inequality, and he says that some of the expectation of these four measurement will always be less than or equal to 2 or greater than or equal to -2. You can also play around with this inequality by providing those values +or -1. You will never able to violate this particular equality in terms of classical mechanics. So next we will see how this can be violated using quantum mechanically. Before that, I want you to understand few things: quantum gate operations, Bell states, and inner products. Let's see what are those operations. First, we will have quantum gate operations. In the very first class, we have seen the different types of quantum gates. Let's start from basics. We all, most of us know this is a ket 0 in quantum mechanics, which is nothing but a column matrix of 1 comma 0. And we also have ket 1, which is value of 0 and 1. Okay, then we have Pauli matrices Ax, Y, and Z. For this problem itself, consider we will focus on X and Z gate. X is also nothing but as a matrix of value 0, 1, 1, and 0. And Z is also a matrix of 1, 0, 0, minus 1. So when X acts on ket 0, this is simply a matrix operation. 0, 1, 1, 0, 1, 0. So we will be getting from this matrix operation, we will get 0, 1, 1, which is again a ket 1. Please follow this equation carefully, which will be very useful when we violating this Bell inequality, purely a mathematical intuition. So please follow this equation carefully. So from here we understood that when X operates on ket 0, we will get ket 1. Similarly, when X operates on ket 1, we will get ket 0, right? So then we'll go on Z acting on ket 0. This is again a simple matrix multiplication. So when we do this, we will get 0 and 1. Similarly, when we'll put Z acting on ket 1, we will get something called as a 0 minus 1. This is something interesting, that when Z act on ket 1, we will have minus of ket 1 state. This particular minus 1 is the eigenstate of this quantum state. So I hope everyone has understand how this matrix operation happening between the quantum gates. So if you are familiar, if you are comfortable with this thing, we will move to another thing called as a inner product. So as for now, we have seen quantum gates operation and its matrix multiplication of gate operation through matrix multiplication. Next, we will see something called as the inner product. Inner product is something when similar, like we know this is ket 0, which is of 1, 0. Similar to ket 0, we have something called as a bra 0, which is a row vector of like this. So when I do inner product is looks like something like this. This is again a simple matrix multiplication. If you do this, you will get a scalar value of 1. When we try to do inner product of ket 1 and bra 1, we'll also get 1. But when we try to do inner product of ket bra 0 and ket 1, we will have 0. You can also check from your end. If you do bra 1 and ket 0, you will have 0. So it seems that this inner product can be formulated something called as a Kronecker delta I and j, which is equal to 1 when I equals to j, and if it is equal to 0 when I not equal to j. So I appreciate you to understand this carefully about this inner product. Let me know if you are not able to understand this inner product, because it is very much helpful while doing this Bell violation. So if you understand this matrix quantum gate operation and inner product, we move to something called as Bell states. Bell state is nothing but a max entangled state of 2 qubit maximum entangled state. This Bell states also we have discussed very deeply in the last 2 sessions. For being a time, I will just represent what are the 4 Bell states. For psi plus and minus square root of 2, 0, 0, plus or minus 1, and another 2 set of Bell states are psi by root 2. So I guess most of us will be very much popular with these 4 Bell states. Again, this is also very much important to consider in our particular session now. So we will take one Bell state which is of psi minus for our problem. So keep remember this particular quantum state for a moment. So we have seen what is quantum gate operation, and we have seen how inner product is performed, and we have also seen what is Bell states and what Bell state that we are going to take in our session. So there is a slight mistake, which is 0, 1 and 1, 0 here. Okay. So now we have understood this. Then next we'll just see what is the setup that is performed for quantum violation of Bell inequality. So previously we had a source. Similarly, here also we have a same source of psi, except the fact that we'll have our entangled max entangled state, which is one of the belt states, psi minus, which is 0 1 and 1 0. Similar to classical setup, we will have Alice and Bob, and this particular psi entangled photon will keep sharing the entangled photon between Alice and Bob. And now the difference comes in classical observation. We took measurement values as +1 and -1, but in quantum we have to take quantum mechanical measurement values. So we are taking our Q as Z1, which is nothing but Z operator or Z gate performed on first qubit, and R as X1, and S as minus Z2 and X minus X2 by square root 2, and T as Z2 minus X2 square root 2. So this setup is, I hope this setup is very much clear to everyone. Please let me know if you are not able to understand until this moment. So we have seen quantum gate operations, inner product, Bell states, and the quantum setup for violation of Bell inequalities. Then we will violate this inequality such that this particular quantum setup will be greater than 2. So in the previous slide we have seen that it will never be it will, in classical, it cannot be greater than 2. It will always be less than or equal to 2. But in quantum setup we are claiming that it will be greater than 2, and I will walk you through the each steps how to violate this particular principle. So let's do this magic with purely mathematics. I promise you, after here I won't use any quantum jargon terms, and I will also literally use pure mathematical notations like zeros, ones, and just the metric operations and plus or minus. But again, you have to follow me very carefully, such that even I may miss some of the signs. So please help me if I miss something here. One of my colleagues is also nearby, Christian. Please help me if I do any mistakes on plus or minus or zeros and ones. So with that setup, our objective is to violate this particular equality QS RS plus RT minus of QT. So this is what we have to violate. Let me take this particular first set of value QS. We know our Q is Z1, and our S is minus Z2 minus X2 by square root 2. If I do the simple multiplication, we will get minus of Z1 Z2 minus of Z1 X2 by square root 2. So this is our QS. So we know in quantum mechanical, if you want to get a value from a system, we have to perform something called as expectation over the system. So to get the value of this, I can make an expectation of psi minus QS psi minus. I hope this is also understood by everyone. So this is a very simple expectation term that we use in quantum mechanics. So we just apply our values into this equation. We have seen our psi minus is nothing but our Bell state, 1 by square root of 0 1 minus 1 0. Okay, we will just include all the terms here. So if you see careful, I have 1 square root 2 here, and I will also have 1 by square root 2 in psi minus. So I'm taking all the square root outside, and I'm making as 1 by 2 root 2. All right. So once I did that, then I will plug all the values here, 0 1 minus 1 0. Then my QS is minus Z1 Z2. Sorry, it's Z2 here, minus Z1 X2 into 0 1 minus 1 0. So let me first solve this particular part. I'll just take this part and rewrite here Z1 Z2 minus Z1 X2 0 1 minus 1 0. So again, if you see carefully, sorry guys. So I'm rewriting this equation, Z1 Z2 minus Z1 X2 0 1 minus 1 0. So if you see carefully, this is nothing but our basic quantum gate operation, which we have seen in the previous slides. So I'm just doing this quantum gate operation. Anyway, for your comfortness, I'm rewriting for this particular equation Z1 Z2, which means that Z1 on first qubit, Z2 on second qubit, and we have minus, and we have one more minus here. This minus and minus become plus Z1 Z2 1 0 and minus Z1 X2 0 1. We have one more minus and one more minus here, so it will become plus Z1 X2 on 1 0. So if I apply Z gate on first qubit, which is 0, I will get 0. If I apply Z on second qubit, I will get 1. However, I will get minus 1. I already have 1 minus outside, so those minus will become plus. So next, I will have my Z1 on first qubit 1, which I will get minus of 1, and Z on 0, I will get 0 again. And second also, I put the minus first. Z1 on 0, I will get 0. X gate on 1, I will get 0, right? Then I will apply my Z gate on first qubit 1, where I will get minus of gate 1, and X on 0, which will again I will get 1. So if I write this equation, I'm having 0, 1 minus 1, 0 minus 0, 0 minus 1, 1. Okay, so if you remember, we solved this particular part. So I'm plugging this part into our equation now, which is 0, 1 minus 1, 0, 1 by 2 root 2, right? Now, if you see carefully, again, this is our, in terms of our inner product. So I'm just rewriting this term again for our convenience. So 0, 1 into 1, sorry, 0, 1, bra 0, 1, gate 0, 1, and minus 0, 1, 1, 0, and minus of 0, 1, 0, 0, and minus of 0, 1, 1, 1, minus 1, 0, 0, 1, minus, and there is one more minus, it will become plus. So 1, 0, 1, 0, minus, again there is another minus, it will become plus 1, 0, 0, 0, minus minus plus 1, 0, 1, 1. So we have seen our inner product. So now let's solve this inner product. Since these two terms are same, so our I and j are same, I can make it as a scalar 1. These two are different, so it is 0. Again, it is different, 0. It is different, 0. It is same now, so I'll make it as 1. It is different, 0. Similarly, these are different, so we'll make it as a 0. So if I rewrite this equation, remember we have 1 by 2 root 2 here. So this equation will become 1 by 2 root 2 into 1 and plus 1, which is 1 by 2 root 2 into 2. So if I cancel out this thing, it will become 1 by 2 root 2, right? I hope you understand until this point. Actually, this is plus, I'm sorry. So if we see, we got our expectation of QS is 1 by square root 2. So we got one particular value, still we had to go for the other values. So, but for time consider, I'm taking my RS. That's, you can also check from your end. RS will also become 1 by root 2. RT will become RT also will become 1 by square root 2. But this QT part is quite different. So I'm trying to solve this QT part alone from my end as well. So if you remember again, what's our Q? Our Q is nothing but Z1. And our T is Z2 minus X2. I hope you are comfortable with inner product and gate operations. So I will be skipping some of the steps here. So if you do this QT now, we will get Z1, Z2 minus Z1 X2 by square root 2. If similar, I'm sorry again. I'm sorry. So if you remember, same way, we can write our expectation value Qt of psi minus. So if you rewrite this equation, 1 by square 2 root 2, we'll have 0, 1 minus 1, 0 of this Z1, Z2 minus Z1, X2 of 0, 1 minus 1, 0. So same way, we'll solve this particular part. If we solve this particular part, we will get Z1, Z2 of 0, 1 0, 1 minus Z1, Z2 of 1, 0 plus Z1, Z2 of 0, 1 plus Z1, Z2 of 1, 0, right? Sorry, this is X2. So yeah, this is also X2. Okay, so if you solve this particular part, you will get something as 1 0 minus 0 1 minus 0 0 plus 1. And if you plug in the first part, 0 1 minus 1 0, we have 1 by 2 root 2. And we came into this inner product terms. If you solve this inner product, we will get of minus 2. And if you cancel these terms, we will have minus 1 by square root 2. So we have our qt as minus 1 by square root 2. If we plug these values into our first equality, inequality, this particular equation, let's see what we are getting it. So we have our qs as 1 by square root 2 and rs also 1 by square root 2, and our rt is 1 by square root 2. Remember, we have minus on our inequality itself, and we have our qt as 1 by square root 2. So if you solve all these terms, we will have first 4 by root 2. Then this can be simplified into 2 root 2. So if you see, this is clearly greater than 2. So we can rewrite our equation as rs plus rt minus qt, which is which which is equal to 2 root 2, which is again greater than 2. So we have now see that this particular inequality cannot be greater than 2 in terms of classical, but we have violated this thing using our quantum mechanical. You may wonder how this thing happens. See, from the beginning, we just use simple mathematics matrix operations, but we are able to violate this particular inequality. This is majorly because of the entangled state that we used as our source, which is of psi of 1 by square root 2 0 1 minus 1 0. So because of this entangled state, we are able to violate this Bell inequality. So Bell states that there is no locality and realism has been violated in this particular equations, and it is and he also suggested any system which violate this inequality, it becomes quantum. So I appreciate you to try for all the other Bell state, which is of phi plus and minus and also psi plus. You can find your own measurement observable for this different Bell states, and this not just work with this particular 2-qubit inequality, it can also work to multi-qubit inequality as well. This 3-qubit inequality we call as a Mermin inequality. It is a separate inequality. You can also check about that. If possible, we also try to share you resource for Mermin inequalities as well. So with this, we are able to see that we are able to violate some inequality using quantum operators, which cannot be done using classically. So this is something which has shown in the very early stage as a quantum advantage over classical. So this Bell violation has been done we are at the end of the Bell violation now. Please let me know if you have any questions in this particular part. I will try to answer that. Or if there is no question, we will move to the next session, which is of solving max cut problem. So I will wait for 1 or 2 minutes in the main to have the questions from your end, and we can move to max cut problem now. So I see no questions from anyone. So no problem. You can play around this Bell violation from your end. It is really interesting part in quantum. It is one of the earlier concept which shows a quantum advantage over classical as well. So if there is no question, we can move to max cut now. Okay, thanks everyone. I take that as a no. Let's go to next slightly quite advanced problem, which is of max cut, and so we'll see the real application of quantum in action in recent days. Max cut is one of the optimization problem, and which can be solved using quantum algorithms such as adiabatic quantum and QAOA kind of algorithms. So in this session, we will solve the max cut problem using QAOA. We'll also First, we will go through what is the Maxcut problem itself. We will define what's Maxcut problem and what is its objective and its application. Then we'll move forward how it is performed, how to formulate the cost function mathematically. Once that has been done, then we will just touch upon QAOA, what is QAOA, how the algorithm is formulated, and how this problem is solved using QAOA. And at the end, we will have a code walkthrough in Qiskit, how to solve this Maxcut using Qiskit. So I'm skipping the introduction part. So let's understand what is a Maxcut problem itself. You can see there is a graph in a slide, and I'm doing some cut over this graph. So Maxcut says that when I'm performing some cut, it should pass through the maximum edges of the graph, or it also can be defined as when the cut has to pass through the edges such that the sum of the weight of the edges of the graph should be maximized. If you are not able to understand, please do not worry. We will walk through the mathematical part as well. Let's understand just a brief about Maxcut now. This Maxcut problem is one of the NP hard problem. Why? Because when you see the solution space, it rises to 2 power n, which is the exponential size of the problem itself. So classically, this problem is kind of impossible, or it is very difficult to solve when we have large number of nodes. So this is a slight essence of Maxcut itself. We will go like what is the math behind the Maxcut now. So I want to understand first what is graph itself to make you a better understanding for this problem itself. So a graph G is something, it comprises of something called as a vertices and edges. So if there is one vertices V1, this is also called as a graph. If I have two vertices which has no edge, this is also called as a graph. And I can have one edge between these two vertices. I can call this as a E1. This is also a graph now. I can have some other vertices V3. This is also a graph. And I can have other vertices V4, which has edge between V1 and E4. And I can also have self edges between the vertices, which also called as a E3 now. So this is the basics of the graph itself. And these graphs are all called as a undirected and unweighted graphs. So if I have a weight for the edges, let's say this E1 can take weight of 2 and E3 can take weight of 1 and E2 can take weight of 3. These graphs are called as a weighted graph. And if I mark some direction towards the graph, this is called as a directed graph now. So, and there are a lot of different types of graph. This is enough for us to understand for the problem itself. However, for the simplicity in this problem, we are going with our undirected weighted graph. Let me draw a simple graph for you to understand better. I'm calling this nodes, or you can call us vertices as a nodes as well. So I can coin this interchangingly, vertices and nodes. Please do not confuse. A, B, C, D, and E, and these graphs has edges, which is weighted edge. So let's say I'm having graph like this, which has weight of 1, 2, 1, 3, 2, and 1. So I hope you understand what is graph now. So then we go representation of this graph itself. There are two primary representation of graph. One, the popular is list, and another is matrix. So computationally, list is most efficient and the matrix is slight efficient when compared to list. So let's see first how graph is represented using list. So I can have a big list. Now let's say there is a node A and B. It has an edge of weight 1. So this means that there is an edge between A and B and it has weight of 1. And I can write another graph A, and there is an edge between A and C which have weight of 1. Similarly, I can write until the end D and E 1. So this is the list way of representation of graph. And another representation is matrix way of representation of graph. Let's say A, B, C, D, and E. A, B, C, D, and E. So when I have a node between these two corresponding, when I have edge between these corresponding nodes, I will mark corresponding weights in this particular matrix. So let's see if there is a node, there is a edge between A and A. There is no edge between A and A, so I mark this as a 0. And there is a edge between A and B, so I mark this as a 1. And there is a edge between A and C, I will mark this as 1. And there is no edge between A and D, so it's a 0, and this is 0. So similarly, I can enter all the other cells of this matrix. If we see, if there is no self loop, this is something called as I showed you, right? This is something called as a self loop. If there is no any self loop in this kind of graph, then we will simply, our diagonal matrix will be 0. So you have to understand some other one other thing. If there is a in terms of undirected weighted graph, if there is a edge between node A and B, which is same as edge between B to A. So you can see A to B and B to A are same. That is why in this matrix, if you see, the weight recorded in A to B and B to A are same. So this will help us when we trying to solve this problem. Please remember this particular part alone. So now we understand what is a graph and how to represent the graph itself. Now we move to MaxCut now. So what MaxCut is saying that these, now my objective is to divide this graph into two subsets. Before that, I am giving my graph values something called as a binary value xi, which belongs to 0 or 1. So my objective is to, I can have two subset S and T. So if my objective is to divide this graph into two subsets. Let's say I'm including my A and B in this particular subset, C, D in this subset. So if my node is in subset S, I assign the value to the particular node as a 0. And if it is in the subset T, I will assign that particular node value as a 1. So if you see, this is one of the cut that has been performed. So if I do a cut on A and B, which means that now A and B are one subset, C, D, E are another subset. So now what MaxCut is saying that when I performing this particular cut, I will count the edges where the cut is passing. So I will count this particular edge and this particular edge, this particular edge, this particular edge. Now I have to add the weight of all these edges, 1 plus 1 plus 2 plus 3, which gives at 5, 6, 7. So similarly, there are different possible cuts, different combination of possible of cuts are there. So I have to calculate all the weight of all the cuts, and I should select the maximized weight of the cut among the different possible combinations. So how this is performed now? Let's say when I have only one node A, I can put my A in subset S and put nothing on T, or also I can put nothing on S and put my A on subset T. So if I have one node, I have two combination of cuts possible. Okay. So let's say I have a node B, I can put my A here, B here, or I can put my B here, A here, or I can put nothing here and put all the nodes in my T subset, and I can put A and B here and put nothing here. So now if you see now, if we have two nodes, then there are four possible combination of cuts possible. Similarly, when you have 3, there are 9, and 4, it is 16. So if you can see there is a pattern is going on. It is says that when you have n nodes, you can have 2 power n possible combination of these cuts. Sorry, right. So this is the most important. That is why in my slide I mentioned that we have 2 power n possible search space for MaxCut problem. So this is quite costly problem to solve using classical algorithm. And when we have very large number of nodes, it seems quite impossible to solve using any non-classical algorithm with given a best supercomputer available now. In general, this is our classical optimization problem, and this is where our best solution lies. In general, in optimization problems, we will never able to approach or achieve this best solution. We will always able to achieve particular point that is which is called as an approximate or optimization point. We can always try to optimize or approximate our problem. So this is the point we are able to achieve even whichever way we are solving, either classical or quantum. But classical may not able to even optimize to this particular point. This is because something called as a Byron plateau. So when we are trying to solve these kind of optimization problems, we have a graph like this. So let me use different color for this. So these points are called as a local minima, and this point is called as a global minima. These are called as a global. These are called as a local minima. There may be the case when we are trying to solve a problem, we may stuck in one particular point, like in local minima, and we may come to the conclusion that this is our best solution, or we may stuck here and say this is our best solution. But the point is, we are never able to reach this the global minima. When we are able, when we get stuck in this particular point, then we call this as a barren plateau. Again, there are a lot of ways to solve barren plateau in terms of classical itself, but quantum solves this efficiently. We'll see how it is solving as well. So you understand, like in optimization problem, we will never able to solve this problem. So one catch or one thing that we can do here is when we have 2n search space. If it is a weighted graph and it is an undirected graph, as I said earlier, if a to b and b to a are same, let's say I'm assigning my binary values, all the a b c d as 0 1 1 0 1, which means that my A and D are in the subset S. So I'm assigning values as 0 to that nodes, and remaining nodes are in the subset T. So I'm assigning the values as 1. So if you see the bitwise complement of this particular binary value, which is 1 0 0 1 0. So in an undirected weighted graph, the bitwise complement subsets are same. So I can safely reduce my search space 2n to 2n minus 1. So it is very important to understand this point as well. Let me know if you're not able to understand this particular thing. So as of now, we have seen what is our graph, what is the max cut problem, and what are the problem that we face in the max cut, and what are the search space of max cut problem itself. Having understood these things, we will now formulate the something called as a cost function of the max cut problem. Cost function is something that we have to formulate for any optimization problems. So if we see logically, if there is a node between I and j, so what I said earlier, we have two subsets which is divided from our graph itself, and the edges connecting between these two subset should be maximized. This is the objective of the max cut problem itself. So if there is a node between I and j, if there is a node between I and j, then I can mark it as so I can take it that into our subset 0. If there is no node connecting these two subset, then I will mark it as a 1. So I hope you understand this point, right? So I can logically rewrite this particular concept as cost function c of x into, for one node I can write as xi minus 1 minus xj plus xj into 1 minus xi. This can be evaluated equals to 1 if xi not equal to xj, and if it equal to 0 if xi equal to xj. So if I try to generalize this cost function for all my nodes, I can relate this cost function as summation over all the edges which is belongs to my edge set, and I can mark xi into 1 minus xj plus xj into 1 minus xi. So if we rewrite this equation, I will get as xi plus xj minus 2xi and xj. So this is of so here, since this xi is belongs to binary variables 0 and 1s, so xi which is equal to xi square, right? So if you try to apply this thing, I can rewrite this equation safely as xi minus xj the whole square. So this is my cost function of over all the nodes of unweighted graph. Now we generalize this into a weighted graph. We can simply add our weight to this particular cost function I and I j belongs to my subset over I and j. So I add my edge like wij, which is a sum of all the edge weight passing through the cut, xi minus xj the whole square. This is the cost function, classical class cost function of the Max-Cut problem itself. Now our objective is to convert this cost function or encode this cost function into a quantum model to solve efficiently using QAOA algorithm. So we'll come back to this point again. So since we have seen the mathematics behind the Max-Cut itself, I hope everyone able to follow me. If you're not able to follow me or you have any doubt, please let me know. I will clear it here away right away, or I can explain at the end as well. So next, my point is, our question will be, why do we need quantum? So we have seen that our classical algorithm has lot of problems like stucking with the global stucking with the local minima, where the point we are not able to get the optimal solution, and our search space is also very high such that it leads to in search space, and it may be beyond the classical computation for large number of nodes. Even if you see, if we have a graph of node 50 vertices, we will be having 1015 possible combination of cuts. So when it seems that when these problems has exponential growth, that's why we call as NP hard problems. So luckily, some of our quantum properties such as superposition and entanglement will help us to solve this problem efficiently. And as I said, these can correlate between the nodes and you can give the better performance than classical algorithm. So as understand, I mean, having understand till this point, we will now understand what is QAOA itself. Then we will solve the mathematics of Max-Cut as well. Sorry. So most people understand that abbreviation of QAOA is quantum approximate optimization algorithm. It is correct. I mean, it is partially correct, but however, the very first QA algorithm is coined as quantum approximate optimization algorithm. But in through upcoming researchers has shown a lot of similar algorithms like QAOA. So this particular initial QA is currently called as a vanilla QAOA, and all these algorithms, these type of algorithms are categorized as again QAOA, which is quantum alternating operator ansatz. So this is the overview of QAOA itself. We will start all the qubits into a superposition using the Hadamard gates, and we will be having two different Hamiltonian called as a cost Hamiltonian and mixer Hamiltonian. This cost Hamiltonian is something where we will be encoding our Max-Cut problem, and this mixer Hamiltonian is something, so quantum state whose ground state is known to us. So our objective is to find the cost function of the find ground state of the cost Hamiltonian, where our best solution of the problem lies. However, since we know the ground state of our mixing Hamiltonian, we can append this two Hamiltonian together and find the parameters of the mixing Hamiltonian using our classical optimizers. So once we are able to find the best solution by figuring out the ground state of the cost Hamiltonian, we are able to extract our solution for the Max-Cut problem itself. So if you see, this kind of setups looks like similar to VQE. Again, VQE also tries to find the ground state of the system itself. So QAOA also worked kind of principle. I mean, QAOA also works based on the principle of VQE itself. So once we understand, we'll just understand the QA workflow now as overview. We have defined the graph now. Okay, before this part, we'll again move to this math part. So you have seen that we have formulated this cost function. Now we'll see how to encode this into our quantum model. So between this classical and quantum, there is one connection which is called as the Ising model. So we will formulate this problem into an Ising problem. Then we can directly encode this Ising problem into a quantum problem. So in simple, this Ising model has something called as a spin. In physics, there is some concept exists called as a spin. So we are not diving deep into concept of spin itself. We are just seeing the mathematicals of spin. So the spin Si belongs, it can take values of either +1 or -1. So there is a general standard template to formulate this classical values into a spin model, which is of Si can be encoded as 1 minus 2xi. Okay, so if I rewrite this equation, I can get xi as 1 minus si by 2. Similarly, for xj, I can have 1 minus Sj by 2. So we'll just encode this into our equation of classical formulation. So this cost function now I'm changing it to C of S. So again, this will be summation I comma j belongs to H set. And if I plug in this values of xi and xj, this equation will become wi and wj, sorry, wij to 1 minus si sj by 2. Okay, I can take this to outside and it will become I j belongs to E wij 1 minus si sj. So this is icing formulation of max cut problem from classical. Okay, now our life is very simple. We can directly move this into a quantum model. Before that, I want you to understand few things. We have something called as a observable in quantum. There are different observable. The main observables are Pauli observables. So we will focus on this Z observable now. When we measure our quantum state Z, we will have either 0 or 1 or plus 1 or minus 1. These plus 1 and minus 1 are nothing but a these plus 1 and minus 1 are nothing but a eigen state of the quantum eigen value of the quantum system itself. Okay, so this is a quantum mechanical concept. So if you see carefully, we can correlate or we can try to understand this Pauli Z observable and spins are quite similar. So I can directly or safely encode this cost function or rewrite this cost function into a quantum model of I and j belongs to H set, and my weight, sum of my weight wij, and this one I can mention as a identity gate, and this is si I will be become as zi and zj, where zi is nothing but my Pauli z operator on ith qubit, right? So we have now formulated into quantum model. So now we have formulated this. This is called as our cost Hamiltonian HC. So now we have to know what is our mixer Hamiltonian. Again, there are a lot of ways to develop the mixer Hamiltonian. We can also come up with our own mixer Hamiltonian based on your problem set. But the standard mixer Hamiltonian is using the Pauli X observable. So this is also nothing but X operator, Pauli X operator on ith qubit. So this is our mixer Hamiltonian. Now we have to append our cost Hamiltonian and mixer Hamiltonian together and optimize this mixer Hamiltonian parameters to get the ground state of cost Hamiltonian. Until I hope and it is clear until this point. The basic formulation will be psi theta, cost Hamiltonian, psi theta. This psi theta is nothing but our mixer Hamiltonian, and this is the cost Hamiltonian. And theta, when I say theta, it has series of parameters, theta 1, theta 2 until theta n, right? So our objective is to optimize these parameters to get the ground state of our cost Hamiltonian. So this is how we have converted our classical max cut problem. First we converted into icing model, then this icing model is converted into our quantum model. So I guess it is clear to everyone. So now we'll move to overview of this workflow of QAOA itself. So first one has to define the graph itself, whether it is weighted graph or unweighted graph or undirected or directed graph, and we have to efficiently represent our graph either in a matrix way or list way. Once that has been done, we can construct our operators, which that we have done now, like formulating the cost function and and converting into cost Hamiltonian and mixing and also defining the mixing Hamiltonian. Once the mixing Hamiltonian and cost Hamiltonian has been defined, we can append these two Hamiltonian into one quantum circuit and append with our classical optimizer, and we try to optimize these parameters using our classical optimizer. So these classical optimizers can be of your choice based on your problem again. So and once that has been optimized, we will use the we will extract the solution by measuring the quantum circuit. So when we measure the quantum circuit, we will again have some set of binary values which can be mapped to our solution. So whichever the binary values has high number of cost value, that will be concluded as the best solution of our max-cut problem itself. Now we will move to code walkthrough of the same max-cut problem. 1 minute, guys. Give me a minute. So I guess we have. I mean, you are in. You are. I mean, you are able to appreciate this problem, max-cut problem itself. So before moving to code walkthrough, I will pause here for 1 to 2 minutes for any questions. If you're not able to understand in any of the part in the max-cut problem, we can revisit and I can clear your doubts. So this is a time for doubt for 1 to 2 minutes. Yes, thanks for the question. No, for every optimization problems, we have to formulate our cost functions. So based on the problems, formulating the cost function differs. But however, once the cost function is formulated, it will be in the variables will be in the binary. So we can easily convert into spin and directly to the quantum model itself. And there are other ways of solving the problem, which is using QAOA model, where we use adiabatic quantum algorithm, where we try to, I can show you that as well. In QAOA, you might have remember like we formulated some matrix right in the beginning of the graph. So I can call this matrix as Q, and I can have some unknown values of X. I will tell you what is this X. Basically, this adiabatic quantum tries to solve it, either minimize or maximize this particular equation X transpose and X. So this Q matrix is something called as a cubo matrix, where our graph weights are encoded, and this X matrix will have X1, X2 until the n. These are unknowns, and this is nothing but X transpose matrix. So what adiabatic method use? It will put different values, this unknowns X, and tries to solve and use the best solution. So to answer your question, the way that I formulated the cost function, this is only for graphs, particularly towards the max cut alone. And for the IC model and quantum model will be similar to a lot of problems.
Bharat,
But remember, like
the
cost
land
function is
of
different for
ancient India.
different problems. Even in the graph, that we have to have different cost functions. Uh, Sorry, guys. So I was on mute. So I guess there is no question. So we will move to the code walkthrough itself. So I have took very simple and a powerful problem, which make you to appreciate how quantum algorithms such as QAOA can efficiently solve the NP hard problems. So we will share this code with you. You can also manipulate and play around this code such that you are able to appreciate these quantum algorithms. So these are the first cell has basic packages that is imported for the problem itself. In the next cell, if you see carefully, where n is a number of nodes in the graph that I have defined. So for simplicity, I have defined it as a 5. So you can also increase your nodes or decrease your nodes based upon your comfort zone. So if you see in the fourth line edge list, which is e list, I have mentioned 0, 1, 2.0, which means that I have an edge between node 0 and 1 of weight 2. So similarly, I have represented all the edges and corresponding weights as well. So you can also increase the number of edges, and also you can increase the weight of the graph as well. So once that has been included, these are just visualization code for visualization. This is my graph visualization. You can see the edges and nodes, and they have encoded with the corresponding weights as well. So now this is the way to express our graph in terms of matrix formation. So this is similar like as we see in the mathematical way. If there is a node between 0 and 1, we have a value of 2. And if you see the bitwise complements like A to B and B to A kind of things, where the nodes edge weights are same here. So once we formulated this matrix and equation, we can try to do the max cut problem using the brute force approach. So if we don't know what is brute force approach itself, in brute force approach, it will try to solve our problem by exploring all the possible solutions. We have seen in MaxCat, we have 2 power n possible solution space. So that's why in the code, if you can see, we have 2 power n in the code. And if you see, these are the possible cut that can be formulated in the given graph that we have defined. So in the first case, 0, 0 represent, there is no cut has been formulated, which gives of cost of cut is 0. And in the second case, we have seen our node 0 alone kept in one subset, and all the other nodes are kept in the other subset, which gives a cost of 5.5. We can see that now, like we go to the graph, if you see, our node 0 is separated into one subset, and all the other nodes are into other subset. So if I perform a cut like that, if you see these edges of weight 2, 1.5, 1 and 1 again will be in the part of the cut. So when I add this edge weight, it will give us to 3.5, 4.5 and 5.5. So that's how we got cost of the cut as a 5.5. So our objective is to get the maximized weight of any of the possible cut. So it seems that in this particular cut, where we have a node 0 and 2 in one subset, on all the other nodes in the other subset, we had a cost of the cut as 8.5. So in brute force approach, we are able to find this as a solution. However, since it is a very simple graph, this brute force approach seems to be really well. But when we try to increase this number of vertices, it will become impossible to get the best possible solution from our end using brute force approach itself. So from this equation, we formed our cost function. So this cost function is represented in terms of quadratic equations here. We just need to encode our graph weight into a cost function that we have formulated in our previous slides. Once this cost function is formulated, if you see, we can directly here in Qiskit, they have a code to formulate this into icing directly. So they have made into operators as identity and ZZ for against respective cuts, respective possible combination of cuts. So once that has been formulated, they have also tried using one of the classical way of optimizing max cut problem, which is using minimum eigensolver technique. So there they have found the same solution that we found in the brute force approach itself, which is 8.5. Again, since this is a very small graph, we are not able to appreciate the advantage of quantum itself here. Now, once we solve using classical algorithm, we move to our QAOA algorithm. So since I say the QAOA has our mixture Hamiltonian, here I represent that as a ansatz, and here I took Qiskit default ansatz, which is of n local, which compromises of rotational gates in direction of Ry and control Z gates, and I had took my classical optimizer as SPSA. So I just append this Hamiltonian mixer Hamiltonian with my cost Hamiltonian through VQE, and I try to solve these problems through quantum mechanically, and I'm able to find this as a best solution. If you see, in classical way, we got 0 and 2 in one subset, but here we have 1 and 3 in one subset, and 2, 0, 4 is in the different subset. So but if you see, we have the same cost function of 8.5. This is majorly depend upon the weight of graph that you have, but however, this will be applicable in a lot of area of application. I will tell you the application of MaxCut at the end of the code. So we have solved using one of the Qiskit answers and classical optimizer as well. I also took another type of predefined answers in Qiskit, which is real amplitude. So I have also used Cobel optimizer. If you see, we got the same solution as we got in the classical here. So here also the cost of the cut is 8.5, which is the best solution for us. So this is how we can encode our problem and solve using Qiskit. So the first set of this structure represent the decomposed structure of our first ansatz, which is n local. You see, we have used our rotational gates and C0 gates here. So here R is nothing but a representation of parameters, and if you and we have a real amplitude circuit as well. If you see here carefully, we have parameters of number of parameters as a theta as a 30 parameters are here. So when we have more number of nodes, or when we have large number of repetitions in this ansatz, we'll have large number of parameters. So I hope you remember in our first session we saw that when we have large number of parameters, it will take a lot of time to find the best solution. And if we have large number of entangling gates, it will also it will increase your circuit depth, eventually reduce your fidelity of the quantum circuit, and you will have less performance when compared to other circuit or classical algorithms. So one should carefully consider when you are designing your QAOA ansatz, you have to consider all the benchmarking technique that has been used in the quantum neural networks. So I can again reiterate that as circuit, you have to consider circuit depth, expressivity of the circuit, entangling capability of the circuit, and also you have to take care of the error correction and mitigation technique if you are appending this circuit with the noise channels in hardware. So we will share this code with you. You can try with different number of nodes of graph and different types of ansatz and different types of classical optimizers. And also, if you are able to do, you can append any noise channels that Qiskit has to the circuit and try to run in any of the available backend in Qiskit, so that you can able to appreciate, or you can able to see the real advantage of quantum compared to the classical methods. Now we'll come to the application of this maxcut itself. This maxcut problem is used in a lot of areas such as social media networking. When we have different cluster of networks, it is able to divide the clusters in clusters efficiently. And if you are from computer networks domain, you can see lot of topology of computers like star topology, linear topology. If there is any issue happen in one particular network, where we have to separate the other clusters from the defective network. So maxcut will help you to classify the cluster in the best efficient way. So these, and also wherever the networks are there, maxcut will be able to solve efficiently in those problems. So these are the applications, some of the application of maxcut problem itself. So that's it for the today's session. So we are open for a Q&A session now. So if you have any questions related to bell violations or maxcut problem, please let me know. I'm here to answer to you. Or if you are not able to reach me here, you can also reach me personally. I will share you resources as well to get the essence and core crust of the problems itself. So we will share the attendance towards the end of the session. So please mark your attendance and with proper name that you want to be on your participation certificate. We will be closing that form like 10 minutes right after the session itself. So this is a time for Q&A. After 2 to 3 minutes, I'm handing over the session to Krishan Sharma.
Thank you so much, Thirumalai, for that insightful and engaging session. Your explanations of bell violation and quantum optimization were truly eye-opening and gave us a clear picture of how theoretical concepts are finding practical use in the real world. So I am sure all our participants have gained valuable insights and deeper appreciation for the power of quantum computing. So if anyone have any questions or doubt, please feel to ask. We will sharing an attendance and a feedback form, Google form, where you can mark your attendance, give the name that you want on your certificate, and also you can give your feedback if you what you like, what you do not like about these 3 days of our Qiskit Fall Fest, so we can improve any further. So yeah, if anyone have any questions or any doubt, please free to ask.
So, ma'am, we have sharing the codes over the mail for all the registered participants. So we took mail IDs from the registration form itself. So we have also shared yesterday sessions solution to the yesterday session code walkthrough. So in the same thread, I will share the mail. So if you're not able to receive the mail, please reach to me or any person from C-DAC Delhi. We will try to share the codes to you over the mail.
Okay. Thank you.
Wait. Okay, I take this as no. There is no questions in the chat box as well. I'm handing the session over to Krishan. Thank you, everyone. Thank you for your active participation. Thanks, Krishan.
So thank you, Thirumalai, and thank you everyone for joining this Qiskit Fall Fest conducted by C-DAC Delhi. So with that, we have reached the final moments of our day 3, and with that, we will conclude the Qiskit Fall Fest. So to conclude this event, I would like to invite our guest, our center head, Sri Jitendra Singh, to share his closing remarks and reflections on this 3-day journey and our vision and commitment to advance the nation in the growing field of quantum computing. Sir, over to you, please.
Good afternoon, everybody. As I hope these 3 days was very informative, and you have very you are going to learn something by these sessions. So, as India accelerates its journey towards technological leadership through the National Quantum Mission, events like the Qiskit Fall Fest are vital. They reflect our deep commitment to nurturing quantum talent and driving innovations. I extend my sincere congratulations and thanks to each of you for participating in this fest at the C-DAC Delhi. I trust that these sessions have been both highly educational and encouraging, equipping you to keep pace with this rapidly advancing technology. Finally, my special thanks goes to Neuro-Cognitive AI and XR Group, and especially to Ms. Priyanka Jain for leading this initiative and contributing so significantly to both the organization and the nation. Wish you all very best and happy learning. Thank you. Thank you very much.
Thank you so much, sir. So these are very kind and inspiring words from our center head, sir, Jitendra sir. Now I will ask our group head, scientist of Dr. Priyanka Jain, to share his insights about this Qiskit Fall Fest and encourage everyone to listen what I have mentioned.
Thank you. Thank you, Krishna. Though I'm not supposed to say any word on that, I just wanted to thank you all, right from the participations which we have received, and it is thoroughly we have received a good number of participation, enthusiasm, QA session, and the feedback from all the participants, and it is really encouraging for us to take the things like this, the events like this forward. That is one thing. I would like to thank to the organizing team, because the new researchers, the young researchers, they came forward with the initiative, and we want to do this, and it is very encouraging, and we should do this, and it is going to proliferate the technology and all. So I thank each one of you, right from Tirumalai, Krishna, Kartike, Aruna, and Jayesh Hire, those who are working behind the curtain as well. Not last but not the least, I really very thankful to Jitendra sir. Sir, with your kind guidance and motivation and encouragement, we could conduct this event successfully. And I'm really thankful to you for your encouragement and motivation every time you provide it to us, for your guidance as well. With this, we are concluding this Fall Fest 2025, which was in collaboration with IBM. Thank you, everyone. Keep learning, happy learning, and have a good day ahead. Thank you very much.
Thank you, ma'am. Thank you, sir. So that's how we concluded this event, and we have shared this attendance and feedback form in the chat. Kindly fill it. We will close this meeting and this Google form at 12:30. So kindly fill it as the name you want on your certificates. Thank you, everyone.
We would like to see the feedback from each one of you in case the possibility of sharing the thoughts, how the event went on, and in case some modification required or some correction for next time, would like to hear in case someone is willing to share.
As is the name you want on your certificates. Thank you, everyone.